PID tuning your 3D printer's hot end is vital, but to get things perfect, we can go further with a few clever tricks. But there's only one problem. I'm not sure if the effort is worth it, and I need your help to decide. This video comes directly from a request from viewer Bob, who asked me a simple question about PID auto-tuning for different scenarios. This really got me thinking, so here is a study on the limitations in our current approach and what I hope might be a better way. Let's start from the beginning. What is PID? Well, it's a control algorithm and it stands for proportional integral derivative. I'm not going to lie, this is complicated, but we only need to understand the gist of it to know how it works for our 3D printer. Before PID control was implemented, our printer's heaters were controlled with bang bang, a simple on-off control method. Let's look at the difference between the two with a simple example. The rocket ship can either be powered or the engine cut off, and if we keep it powered until our target height, it's going to overshoot. Same goes if we don't power the rocket until it's falling to our target height, it's going to undershoot, and the result will be oscillation. If our 3D printer's hot end or bed is treated the same way, where the heater is kept on 100% until the target is reached, we'll see a similar temperature overshoot and then a similar dip after the heater is turned on once the temperature falls below the target. PID control is vastly superior once tuned. If we come back to our rocket analogy, the first thing that happens is that it's smart enough to turn off the engines before the target because the inertia of the rocket is taken into account. The system also has the ability to apply partial throttle if that gives more precise control. Let's demonstrate the difference with PID auto-tune by setting the heater on this 3D printer to 200 degrees, and we can see at the start that the heater is given 100% of its available power and the temperature rises quickly. This means we don't have any unnecessary delay. However, once we hit around 190 degrees, we can see that the state drops below 100%, quickly dropping down to around 30 or 40%. The PID algorithm knows that we'll overshoot if we keep 100% power on, but knows that we'll undershoot if we drop it all the way to 0. So it modulates the power to make sure we only go around 2 degrees over. Fast forward a minute or so later, and we can see that the temperature graph is pretty stable. The plot looks like a horizontal line rather than having any oscillation. This is the PID control algorithm doing its job. Let's peek behind the curtain for this particular printer. And if we come to the end of this Clipper config, we can see for both the extruder and the bed that the control method is listed as PID with the P, I, and D values for each. All good so far, but what if these values are wrong and how do we find them? Firstly, if the numbers are wrong. If you search online, it's easy to find examples of people's temperature graphs that either oscillate or are quite erratic, despite the control algorithm being PID. And recently I had my own example of this when retrying non-planar printing, fitting an alternate airbrush nozzle which pretty much looked the same, apart from this very pointy protruding tip on the end. But that was enough until I retuned the PID values to give this wild oscillation that meant the print never actually started because the hot end was never able to settle on the target temperature. The good news is it's very easy to tune this, in fact the printer will do it for us. I've already made a video on this and it's embedded in a page of step-by-step instructions on my free calibration website. Let's quickly do an example in Marlin then Clipper, and in Marlin we use the G-code M303. We simply enter this G-code into the terminal with some parameters. E0 meaning extruder 1, S200 meaning a target temperature of 200, and U1 meaning we'd like to save the result to the EEPROM once the tuning is finished. The process will start and we'll see the temperature start to rise on the temperature graph. Once the tuning starts, we can see that the printer's firmware is experimenting with oscillating the power to try and maintain the target temperature. By default, Marlin will do this for 5 cycles, and for each, the PID values will be spit out into the console. We can see from the graph that the accuracy is improving as the values are tweaked. And when all of the cycles are done, the determined P, I, and D values will be given to us to save to the printer's configuration. Clipper's auto-tune works exactly the same way, but the command is called PID_calibrate. Again, we paste this into the terminal, set our heater, most likely the extruder, and then our target temperature. After we send the command, the process is automatic. Like Marlin, it will go through several cycles and then spit out the P, I, and D values, ready for us to save to our config. This is a well-established system, so you might be thinking, how can we do it better? And that brings us to Bob's question. To paraphrase, he asked, won't the conditions for PID control change at different parts of the print, potentially resulting in temperature fluctuations? More specifically, Bob referenced part cooling, which depending on the filament is blowing across the nozzle for most layers that we print. Yet typically this fan is turned off for the first few layers of the print to help the plastic adhere to the bed. There's probably more, but here are the variables I can think of that affect PID control. Firstly, the thermal mass of the hot end. Typically hot ends have a big chunk of metal called the heater block with a heater cartridge and the nozzle attached to it. The more thermal mass, the slower this will be to heat up, but the longer it should retain that temperature. Our next variable is the heater power. We have different heater cartridges with different wattages, and the more power we have, the faster we can expect the hot end to heat up. We also have ceramic heater cartridges where the same principle applies. Next, we have loss of heat into the filament. This is the job of the hot end, to transfer heat into the filament to melt it so it can flow through the nozzle. And the greater the filament flow we have through the hot end, the more heat it's going to sink, and the greater the heater power will need to be to maintain the target temperature. Finally, we have the loss of heat into the surrounding air through convection. This happens all of the time, but is exaggerated when the part cooling fan is blowing air across the nozzle. More heat is required to maintain hot end temperature, and obviously a silicone sock will make a big difference here, insulating the hot end and retaining the internal temperature. If we come back to our earlier airbrush nozzle example, there should be a bit more thermal mass from the extended tip, but then a different material and more surface area on the extended part to make the hot end cool more quickly. And as we saw, this visually subtle change was enough to throw out the PID parameters completely. In my PID autotune guide and most others, the instruction is given to turn the part cooling fan to maximum to better match printing conditions with PLA at least. And it makes sense because we want the temperature as stable as possible during the majority of the printing process. But surely that's leaving some optimization on the table, as we have a range of materials and conditions that we print at, and we're really only tuning PID for one of them. Luckily, we can auto-tune for these different scenarios and apply the right settings at the appropriate time. The first step is to make a list of any specific scenarios your printer might encounter. And then for each of these, run the PID auto-tune for your firmware of choice. Just remember to turn on the fan to the percentage you're after before running the auto-tune command. Pretty much every firmware uses M106 for this, with S255 being 100% fan, and S128 being 50% fan. And you can change the S variable to suit any other percentage you want. When the tuning is done, rather than storing the values, we're going to write them down somewhere safe. And we repeat this until we have P, I, and D values for all scenarios we're after. In Marlin, our job is easy because we can use the M301 G code to set the hot end PID at any time we want, including partway through a print. The documentation makes it look more complicated than it is, because all we have to do is enter M301, P followed by our P number from earlier, I followed by the I number, and D followed by the D number. Once we send the command, the PID values are updated on the fly. Unfortunately in Clipper, there doesn't seem to be an equivalent command, and it has been requested on GitHub, and despite some discussion and even a pull request, nothing ever came of it. So the best we can do with these values is to input them into our config, changing them before we print with a different material. In Prusa Slicer and Derivatives, we can automatically set the PID settings per filament by coming to Filament and then down to Custom G-Code. And all we need to do is paste in our M301 command in the Start G-Code section. And we can search in the exported G-Code to find M301 with our new PID settings inserted just after the Start G-Code. So if we like, we can set this up for each filament so that our PID settings are always exact. Orca Slicer and Bamboo Studio work exactly the same way. We can open the filament preset, come to Advanced, and input M301 ahead of any other G-code in that section. Cura unfortunately doesn't support this, so the best I can think of is to put it into the Start G-code and then save copies of the same printer for each material. Let me know in the comments if you have a better way. And finally, back to Bob's query, changing the PID at various times to suit different part cooling. For this one, we need to PID auto-tune for two scenarios. Our first layer temperature with the fan off, and then our hot end temperature with the fan set to whatever we normally leave it at. For this trick, we're going to be referencing this setting, disable fan for the first amount of layers which we specify, and this is pretty common in most slicers. We'll start with Prusa Slicer, and we want to come to our printer's start G-code and enter our M301 command with the PID values for when the fan is not running. We'll then scroll down to the after layer change G-code and use some conditional G-code as follows. If the layer number equals the disable fan for first layers, insert this code, and that includes the M301 with our PID values for when the fan is running. And don't worry, you don't need to copy from the screen. I've got this as well as the examples to follow in a paste linked in the description. Let's inspect the G-code that we exported from Prusa Slicer. We can see before the print starts, our PID values for no fan are loaded ready for the first layer, and if we search down layer by layer, once we get to layer 4, which is at 0.8mm, our G-code is inserted with the PID values for when the fan is running, and we can see the fan coming on just before that. The beauty of the system is we can change this value and everything else will automatically update. Now let's try Auger Slicer with no cooling once again set for the first 3 layers. Like with Prusa Slicer, we're going to come to our start G-code and enter our M301 command with the PID values for the fan off. We'll then scroll down until we reach layer change G-code and enter a very similar piece of conditional G-code to Prusa Slicer, housing an M301 command with the settings for when our fan is on. Once more, let's examine the output G-code, and we can see our PID set for no fan at the start, and then as we go down through the layers, we'll see that when we get to layer 4, 0.8mm, our M301 command is inserted for when the fan is on. In Cura, we'll once again need to edit the start G-code and paste in the M301 for when we have no fans running. From this point onwards, we rely on a community post-processing script. It's by 5 axes and it's called insert at layer number. I've linked this repo which has instructions on how to install this, but basically we just paste the file in a specific place for the Cura install and restart Cura. Now we come up to extensions, post-processing and modify G-code. We then add a script and select insert at layer number. And now we tell it before layer 4 and paste in our M301 command with the values for when the fan comes on. When we slice, we'll have a symbol here showing us that the post-processing is in action. And when we inspect the file, we can see that M301 is in the start G-code, and then later in the file, just before the part cooling fan comes on, the appropriate M301 command is set to get the ideal PID settings. This works, but the only problem is we'll need to update our script anytime we change this parameter in the slicing profile. And that's how I would conditionally set hot end PID control parameters. I'm just not sure it's worth it given the discrepancies in firmwares and slicers. If your printer is sensitive and the hot end fluctuates easily, then maybe you should try this out. I think in future a better way might be for the firmware to test for these different scenarios and store different PID values that it can switch to on the fly, automatically detecting when the fan comes on and perhaps even how strong. Let me know what you think of that idea as well as what you've seen in this video in the comment section below. Thanks to Bob for the request, thank you for watching the whole way through, and until next time, happy 3D printing. G'day, it's Michael again. If you like the video, then please click like. If you want to see more content like this in future, click subscribe and make sure you click on the bell to receive every notification. If you really want to support the channel and see exclusive content, become a patron. Visit my Patreon page. See you next time.